Welcome to the Explainer. Today, we are diving into something absolutely fundamental. We're talking about motion in a straight line. We're going to break down exactly how to measure movement and, honestly, the coolest part, how to mathematically predict exactly where an object is going to be in the future. Let's get right into it. Okay, here's our roadmap for this Explainer. We're covering position and displacement, speed versus velocity, understanding acceleration, graphing straight-line motion, the all-important equations of motion, and finally, a quick intro to relative velocity.
So, part 1, position and displacement.
Before we can even talk about moving, we have to know exactly where something is, right? To measure that, physicists use what's called a frame of reference. Think of it like standing on a specific street corner with a stopwatch. You've got a designated spot to look from and a way to track time. It's essentially a set of 3 mutually perpendicular axes, x, y, and z, that let us pinpoint a location in space. And because motion happens over time, we absolutely need that clock. Together, the coordinate system and the clock form our frame of reference. If an object's coordinates don't change over time relative to your street corner, well, it's at rest. If they do change, it's in motion. Pretty straightforward. And this brilliantly illustrates exactly what we're talking about. We have our x, y, and z axes right alongside our all-important clock keeping time, which we mark with a T. Notice how a particle starting at point P has its own specific x, y, and z coordinates. Then it moves along a path to point Q, and bam, it has entirely new coordinates, x prime, y prime, and z prime. This maps out perfectly how movement is, at its core, just a change in coordinates within our defined reference frame over a certain period of time. Now, as that particle actually moves from point P to point Q, we have to distinguish between 2 incredibly important yet very different concepts: path length, which you usually hear called distance, and displacement. Path length is the actual total length of the journey. Say you wander all over your house, going from the kitchen to the living room, down the hallway, and finally to the front door. Your path length is quite long. Displacement, however, is simply a straight line from your starting point to your ending point. It literally only cares about where you began and where you finished. It's the shortest distance. Now, in one-dimensional straight-line motion, these two are only ever equal if the object never ever changes direction. If it reverses course even once, the actual path length will always be greater than the magnitude of displacement.
Moving on to part 2, speed versus velocity.
Let's look at this comparison. Uniform motion is kind of our idealized scenario here. An object covers equal distances in equal time intervals. That means its speed and velocity remain perfectly constant. And because that velocity isn't changing, the acceleration is exactly 0. It's highly predictable. It's like a car locked on cruise control on a perfectly straight, totally empty highway. Non-uniform motion, on the other hand, represents the messy reality of the real world. You've got unequal distances covered in equal times, varying speeds, changing velocities, and non-zero acceleration. Just think of the absolute frustration of getting stuck in stop-and-go traffic, constantly hitting the gas and slamming on the brakes, or even just a person walking down a crowded sidewalk at varying speeds. So if your velocity is constantly changing in that messy, non-uniform way we just talked about, how do you know your exact speed in a frozen fraction of a second? Well, think of a car's speedometer. It doesn't show your average trip speed, it shows your instantaneous velocity. This is the exact velocity of an object at one specific exact moment in time. But to actually calculate it mathematically, we have to bridge basic division with calculus, using something called a derivative. Now, what's really interesting here is how advanced math steps in to save the day. The concept of the differential coefficient, or derivative, gives us the precise tools we need to find that exact speed. See, while average velocity is just total displacement divided by total time, instantaneous velocity uses calculus to shrink that time interval down to almost exactly 0. It essentially freezes time to give us a perfect snapshot of motion. This allows us to flawlessly describe the physical quantities involved in changing motion at any given instant.
That brings us to section 3, understanding acceleration.
If velocity is the rate of change of position, acceleration is the rate of change of velocity. It's what makes motion truly dynamic. First off, acceleration only happens when velocity actually changes over time. If you're cruising at a constant 50 miles per hour in a straight line, your acceleration is a big fat 0. Second, just like motion, acceleration itself can be uniform, meaning it's a constant, steady value, or it can be changing. Third, since we're strictly dealing with one-dimensional motion along a straight line today, positive acceleration generally means the object is speeding up in our chosen positive direction. And finally, negative acceleration, which you'll sometimes see referred to as retardation in physics texts, means the object is slowing down. It's literally the brakes being applied to our velocity. let's move to section 4 and see how this all builds visually, graphing straight line motion.
Physicists absolutely love graphs, and for good reason. They tell the entire history of an object's motion at a single glance. Let's start by looking at displacement time graphs. Time is ticking away on the horizontal x-axis, and displacement is tracked on the vertical y-axis. When the line on the graph is perfectly flat and horizontal, displacement isn't changing at all as time ticks by. The body is stationary. It's completely at rest. But when we see a straight diagonal line sloping upwards, displacement is increasing at a steady, predictable rate. This is our uniform motion with a constant velocity. And remember this key takeaway. The slope of a displacement time graph actually gives us the velocity itself. So if the line is a curve bending upwards, the slope is getting steeper and steeper. That means the velocity is increasing. That curved line instantly tells us that constant acceleration is happening.
Now, if we swap that y-axis over to velocity, the story changes completely. A flat horizontal line here now means the velocity isn't changing, it's constant. Notice how a flat line meant at rest on the last set of graphs, but here it means constant speed. A straight diagonal line sloping up means velocity is increasing steadily. And just as the slope of the previous graphs gave us velocity, the slope of a velocity time graph gives us average acceleration. So, an upward slope? That's constant acceleration. If the line is sloping downwards towards zero, the velocity is dropping, which means we're looking at constant retardation, or slowing down.
Finally, let's look at an acceleration time graph. Here, a flat horizontal line means the acceleration itself is a constant, steady number. It isn't changing. We can also map out acceleration increasing over time with an upward slope or decreasing with a downward slope. But for introductory physics, that flat line, representing constant acceleration, is absolutely the most important foundational concept to grasp. It sets the stage for everything that follows.
Which leads us perfectly into section 5, the equations of motion. We're about to translate those physical concepts and graphs into the most important predictive tools in physics. But before calculating anything, we have to lock in our variables so the math perfectly matches the physical realities we just learned. U stands for the initial velocity of the object. V is the final velocity. A is our uniform, constant acceleration. S stands for the displacement, and T is the time taken during the motion.
Okay, here they are. These are the 3 foundational kinematic equations for uniformly accelerated motion. The first equation relates velocity, acceleration, and time together. The second equation allows you to calculate the exact displacement of an object based on its starting speed, time, and acceleration. And the third equation relates final velocity directly to displacement, without even needing to know the time. So the crucial point is this. As long as the acceleration remains constant, these 3 formulas allow you to flawlessly predict an object's future motion. They are literally a physicist's crystal ball.
Finally, let's briefly pivot to section 6, an intro to relative velocity. Here is a wild thought. Rest and motion are completely relative states. It depends entirely on who is watching. Imagine you're sitting on the speeding train. Relative to the seat you're sitting on, your velocity is 0, right? You're at rest. But to someone standing on the platform outside watching that train zoom by, you are moving at a very high velocity. Therefore, an object can literally be simultaneously at rest in one frame of reference and in motion in another. It's all about perspective.
Which leaves us with this final question to ponder. If velocity and displacement rely entirely on your chosen frame of reference, how do all of these kinematic equations we just learned change if the observer taking the measurements is also accelerating? It's a question that pushes us way beyond simple uniform frames of reference and opens up a whole new exciting world of physics to explore. Thanks so much for joining me on this explainer, and I'll see you next time.